But just set the stage.
Yeah.
So you have data from the early universe.
Yes.
You get a Hubble rate.
You get
the traditional galaxies, usually with supernova or some other standard candle.
Yep.
And those two numbers do not match.
They do not match.
In my day, measurements of the expansion rate of the universe differed by a factor of 2. A factor of 2.
Yeah.
And so now they differ by just a few percent.
Right.
But
the error bars,
the uncertainty is way smaller than the difference in those two measurements.
Right. Yeah.
So that is a more severe fact than not knowing the expansion rate of the universe by a factor of 2.
So we had a similar problem with the ages of stars and the age of the universe, which depends
I remember that
on
one.
the Hubble thing, right? And so it was the cosmological data that had to be adjusted.
Somebody found stars that were older than the
That's
universe.
right. Stars in the halo looked like they were older than the age of the universe, right? But then,
and the headlines were, catastrophe! Oh my God!
We all know nothing.
Yeah, people like ready to give up on the universe.
Right. But then we realized, oh no, our cosmology needs to be improved. And so, what happened in the 90s, really, post Kobe, that changed everything in cosmology, right? And then
Not Kobe Bryant.
Not Kobe Bryant. The Kobe satellite.
What you mean right at that game after he got 80, he scored 81 points? That game.
No, not that game.
So the Cosmic Background Explorer, one of the first high precision measurements of the cosmic background.
Mather and Smoot.
So to do it,
Nobel laureates.
Nobel laureates. Yeah.
So circling to the Hubble tension.
So tell me, what's something's got to give?
Yeah, something's got to give. So I think that there's something that we don't understand. I think I'm trusting the measurements, and I think that I trust the theory.
The measurements look good, don't they?
The measurements look good. I was involved in supernova cosmology, right? And also weak lensing studies for looking at structure of growth and these sort of things. And so all this different data, there's more than one probe, right? People are using different types of stars.
Right, that's where you get the confidence from. It's not just one data point from one telescope.
So what James asks is there some physics we just haven't yet discovered?
Are we missing physics, or we just have to adjust the model?
Well, people coming up with these models that maybe the expansion rate of the universe, we have it like, okay, there's this initial impulse, right? And then the universe evolves based on the energy densities of the constituents, of which there are 3 main ones, right? Radiation, which is stuff that moves very fast through space, but almost not at all through time. Matter, which moves very fast through time and almost not at all through space. And space-time, which has its own energy density that we call dark energy, which doesn't move through either one, right? And so initially radiation dominates, then matter comes to dominate, then dark energy, i.e. space-time energy density, comes to dominate.
We think.
That's what he think, right? And each one, you can look at what the expansion rate would be of the universe. But here's the thing.